Today we will continue our discussion about Fourier series representation of continuous time periodic signals. As you remember, last time we said complex exponential signals are eigenfunctions, and they are very useful, especially in Fourier series analysis, as we discuss in this lecture. First of all, just to refresh from chapter 1, the concept of periodic signal. A signal is said to be periodic if x of t is equal to x of t plus capital T for some capital T, which is a positive number. So if this relationship is satisfied for all time t, small t, we call t is the period of the signal, and the smallest value among all t's is called the fundamental period. And we write the frequency in the angular frequency omega naught is 2 pi over capital T, where capital T is the fundamental period. For example, cosine and sine signals are periodic signals. Okay, as you remember, a periodic signal is a signal which repeats itself. For example, this is one example. This is the shape of the signal, and it repeats every t. So capital T is fundamental period. Now, for periodic signals, the Fourier basis functions or the eigenfunctions are harmonically related complex exponential signals given by phi k of t is e to the power of jk omega naught t, where omega naught is 2 pi over t, and k is 0, plus or minus 1, plus or minus 2, etc. So the Fourier series analysis for periodic signal is x of t is equal to summation of from k minus infinity to infinity ak times e raised to jk omega naught t, which means I can decompose the signal x of t into its frequency components. So, and add all those frequency components, we can synthesize the original x of t by adding all the frequency components by using this formula, that means. Okay, when k is equal to 0, we get the DC part, the constant part. And when k is plus or minus 1, we have the fundamental or the first harmonic component. When k is 2, we have the second harmonic, and when k3 is the third harmonic, and so on. So to write x of t using this form, of course, we need ak. How we calculate ak, we'll discuss this in this lecture. Okay. Now, given the signal x of t as a summation of as a summation of ak e raised to jk omega naught t, then what is the ak? Let's prove this, how we get the ak's. So if we refer to also the additional lecture notes here. So if x of t is given by this, what are the ak's? So this these steps will show you how we find the ak's. Okay. Now, without loss of generality, we can multiply the left side and the right side by the same number. For example, we multiply the left and the right by e to the power of minus j n omega naught t, where n is integer. Okay, when n is integer, so the left side and the right side. The right side, because I have two exponential functions here, I can combine it, and I can have this e to the power of j k minus n omega naught t. And the left side is this one again. Now we can integrate the left and the right side. For example, we can integrate over one period, okay? So we can see the result when we integrate. So integration over one period of the left side from 0 to tx of t e raised to minus j n omega naught t, and integration of the right side also from 0 to t of this. Okay, this is the integration. So the summation can go outside of the integration. Okay, so summation, that means we rearrange this part. So summation of k minus infinity to infinity ak, and the integration of this part from 0 to t. So what is the integration of from 0 to t e to the power of j k minus n omega naught t dt? Remember, k and n are integers, right? So k and n are integers. Let's say k is equal to n. When k equal to n, okay, because this is, which is a variable varying here, k is the only one varying, but n is fixed. Remember, n is fixed here, k is varying. So let's say k is equal to n, then this will be e to the power of 0. E to the power of 0 is 1. So the integration of it will become the integration from 0 to t of dt, which is equal to t, and from capital T to 0, I will get capital T. Okay, so the right side integration will become capital T, and this summation, okay, this summation is, of course, when k is equal to n, this will be an. An, okay? So when k different from n, what about from k different from? So the summation will when k is equal to n, this is from k minus infinity to infinity, this is an times capital T. That means when k different from n, what is the integration of this? The integration of this is by using the integration of the exponential function. It will be 1 over j k minus n omega naught e to the power of j k minus n omega naught t from capital T to 0. Okay, so from capital T to 0, that means at capital T it will be e raised to j k minus n omega naught capital T, at 0 e power of 0 1. So what is omega naught times t? Omega naught times t means omega naught is 2 pi over t. So t will cancel t, and I get e raised to j 2 pi k minus n. So e raised to j 2 pi k minus n, using Euler identity, when I expand it, it means cosine 2 pi k minus n plus j sine 2 pi k minus n. Then the sine part, remember k and n are integers. The sine part, sine of the function multiplied by, it's a multiple of 2 pi, so the sine part will become 0. The cosine part will become 1. Okay, so for k different from n, the result will be 1. So this means 1 minus 1, this is 1, 1 minus 1 is 0. So for k different from n, the integration will be 0. That means this this integration will become 0 for k different from n. So the result will be 0 for k equal to n. So for that particular k is equal to n, this ak will become an. So the right side will be an times capital T. An times capital T. So the right side will be an capital T. So now we need an. So that means an is 1 over t, the integration from 0 to t, x of t, e to the power of jn omega naught t dt. Okay? So I have n here, and I have n here. I can change it to any other variable. So because we are working with k, change it to k, this k, and this will become k. So ak will become 1 over t from 0 to t x of t multiplied by e raised to jk omega naught t dt. Therefore, in general, the a case, how we can calculate a case? The a case can be calculated as 1 over period, the integration over 1 period, x of t multiplied by e raised to minus jk omega naught t dt. Okay, here we did the integration from 0 to capital. We can make more flexible the integration interval. So we write as t means integrate over 1 period. This 1 period can be from 0 to capital T, from minus t over 2 to t over 2, or whichever convenient for us. Okay, so this is how we get the AKs, the eigen functions, the constants for the eigenfunctions. So we summarize, let's summarize Fourier series representation. Any continuous time periodic signal can be represented by Fourier series, and the Fourier series representation is a case, and x of t can be decomposed into the frequency components and can be written as a summation from k minus infinity to infinity ak raised to jk omega naught t, where omega naught is 2 pi over fundamental period. This equation is called the synthesis equation because the signal x of t can be built from the frequency components. That's why it is the synthesis equation. How we get AKs? AK can be found by using this formula. We call this the analysis equation. AK is 1 over a period, integrate over 1 period, x of t times e raised to jk omega naught t dt. So this is how we get the AKs. Okay. Now we can have some examples. So the Fourier series now representation means I have x of t here. I write it from k minus infinity to infinity, ak e raised to jk omega naught t, where omega naught is 2 pi over t. When I expand this, writing in long form, when k0, I have a0 times e power of 0, this will be a0. When k1, a1 e to the power of j omega naught t. When k2, a2 e raised to j to omega naught t, and so on. Okay. So what are these AKs actually? When k0, I have a0. A0 means when the frequency is 0. We call a0 the DC component. When k1, we have a1. A1 is referred to omega naught in frequency f naught. We call the first harmonic. When k2, the component of the second harmonic. When k3, the component of the third harmonic. Okay, let's do some examples. Simplest example is sine and cosine. This one, we don't do the integration for this. If we do, we'll get the same result, but we can use directly the Euler identity. Okay, to get the AKs. We just rewrite x of t using the Euler formula. Okay, remember sine theta is 1 over 2j e raised to j theta minus 1 over 2j e raised to minus j theta. So we use that identity. So without performing this integration, if we perform this integration also, we'll get the same result. We can do it directly. So a0, the DC component here, we do not have DC because it's sine only, is 0. A1 is the coefficient for e the power of j omega naught t, because as you see from the formula, the coefficient of e j omega naught t is A1 here. So A1 is 1 over 2j. 1 over 2j when j go up minus j over 2. So I can write it in polar form. In polar form means magnitude and phase. So minus j means e to the power of minus j pi over 2. So the angle is minus pi over 2. Okay? So this is A1. A minus 1 is negative 1 over 2j. J is down. J is down. When j is goes up, so this will be j over 2. So 1 over 2 e to the power of j pi over 2. So I have the plot as a function of k. Usually we plot as a function of k. The rest of AKs are 0 except A minus 1 and 1. The magnitude is of A minus 1 is half and A1 is half. The rest of AKs are 0. That's why we put here dot 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 0. And the phase angle at 1 when k is 1, it's minus pi over 2. And when k minus 1, it is pi over 2. And the rest of the phase is equal to 0. Okay, so I have another example here. X of t 1 plus sine omega naught t 2 cosine of omega naught t cosine of 2 omega naught t pi over 4. Again, find the AKs. So what should we do? Again, we use the Euler. We don't do the integration. So the Euler, change this sign to 1 over 2j e raised to j omega naught t minus 1 over 2j e raised to minus j omega naught t. Change the cosine to, there is 2 here, a factor of 2. So 2 will cancel the 2. And I have cosine, 2 cosine of omega naught t becomes e raised to j omega naught t plus e raised to minus j omega naught t. Then I have this part. So using Euler, I have half e raised to j to omega naught t plus the phase angle pi over 4, but we split it into 2. So times e raised to j pi over 4 plus half e raised to minus j to omega naught t e raised to minus j pi over 4. Now we do this. We have the DC part 1. We combine the e raised to j omega naught t. The e raised to j omega naught t, I have it here and I have it here. So we combine the two. When we combine, I have 1 plus 1 over 2j. Okay, the e raised to minus j omega naught t. The e raised to minus j omega naught t part, I have 1 here, coefficient, and I have negative 1 over 2j. So this is 1 minus 1 over 2j e raised to j omega naught t. And this part is no need for combination. So I have these two terms again. So now I compare with the expanded formula, this formula. Okay, remember this formula, and to determine the AKs. So what is A0? Is there any constant? Yes, we have constant 1. A1, 1 plus 1 over 2j, which means j is down, 1 minus j over 2. And we can write it in polar form. So magnitude and phase. So the magnitude of this is square root of 5 over 2. The phase is minus tan inverse of 1 over 2. A minus 1, 1 minus 1 over 2j. So 1 plus j over 2. Again here, the magnitude and the phase. A2 is the coefficient of e raised to j to omega naught t. It will be half e to the power of j pi over 4. A minus 2, half e raised to minus j pi over 4. Then we write it in terms of magnitude, we plot it the function of k. So what we have a0, we have a1, we have a minus 1, we have a2, a minus 2. The rest of the ak's are 0. So a0 is 1, the absolute value or the magnitude, square root of 5 over 2 a1, square root of 5 over 2 a minus 1, and a2 is half, a minus 2 half. If you see this, it's symmetric about 0. Actually, it is the magnitude is even function. And the phase is this one, pi over 4, the function of k here, at 2, pi over 4, at 1, minus 0.46. Note that this, you can plot the phase angle in terms of degrees or in terms of radians. In this case, we plotted the AKs in terms of radians, because I have here pi over 4 and here minus 0.46 radian, and at minus 1, 0.46 radian, and so on. Okay, this is the plot. And if I have another example, here I have a sum of two, one cosine and one sine, 5 plus 2 cos pi over 2t plus 3 sine 5 pi over 4t. If you have this kind of problem, what you do first? You need to determine the fundamental period, okay? And from the fundamental period, we determine omega naught, because the first thing is we need to determine omega naught, because when we expand, remember the formula, it's a function of omega naught, like omega naught to omega naught, 3 omega naught, and so on. So we need to know the omega naught. So here, I have this cosine part and sine part, 2 omegas. Let's determine the fundamental period. We can use the concept of chapter 1. The period for the first one is 2 pi over omega 1. Omega 1 is pi over 2, so it is equal to 4. That means it is periodic for 4, 8, 12, 16. The second one, 2 pi over omega 2. Omega 2, 5 pi over 4. It will be, T2 will be 8 over 5, so it is periodic for 8 over 5, 16 over 5, 24 over 5, 32 over 5, 8. So we select the common for T1 and T2. The smallest common is 8. So the fundamental period is 8. And omega naught is 2 pi over 8, which is pi over 4. So it's like that. Then we expand x of t using Euler. When we expand using Euler, we get this. Okay, you can follow this. Then we determine each of them, like what is pi over 2 in terms of omega naught? What is minus pi over 2 in terms of omega naught? What is 5 pi over 4 in terms of omega naught? Because omega naught, we already got it here. That's why we found first omega naught. Omega naught is pi over 4. So if you compare with pi over 2, it will become 2 times omega naught. And minus pi over 4, minus 2 times omega naught. 5 pi over 4, 5 omega naught. So by this way, when we write this way, then we will find the corresponding AKs, okay? Because now the DC part is 5, and A1, is there A1? To know whether there is A1 or A minus 1, is there a term with e to the power j omega naught t? We don't have. So A1, A minus 1, 0. A2 is the coefficient of e to the power of j to omega naught t. It is 1, the same as A minus 2. Okay, A minus 2 is the coefficient of e to the power of j to omega naught t. A3 and A minus 3, 0. A4, A minus 4, 0. And A5, 3 over 2j, and we write it in polar form, 3 over 2 times e raised to minus j pi over 2. Then we plot it as a function of k, right? the magnitude and the phase, like before. So for the others which are not available, we make 0. So here, for example, A0 is 5, A2 is 1, A minus 2 is 1, and so on. This is the magnitude plot. The phase plot, all are 0 except at A5 is minus pi over 2 and A minus 5 pi over 2. Minus pi over 2 means minus 90 degree, pi over 2 means 90 degree. Okay, now so far we have a simple sine and cosine signal example, but let's have now a little more complex signal. The first example is a square pulse. Let's find the Fourier series representation of a square pulse. This pulse signal is equal to 1 between minus t1 and t1 and 0 afterwards, but it will repeat. This pulse is repeated again every period t. So when I repeat this pulse after t, the center here is 0. The center here will be t, and to the left this edge will be t minus t1, and this edge will be, the right edge will be t plus t1, and in the negative part also the same. The center will be minus t, and the right edge will be minus t plus t1, and the left edge minus capital T minus t1. Okay, so anyway, this is a square pulse, periodic square pulse, and it's periodic. How we know? From the graph. So always from graphs you can easily for some signals you can easily know the period. Okay, so this is the square pulse. Let's find the AKs. AK, this is the formula 1 over t integrate over 1 period x of t times e raised to j k omega naught t dt. Now we can select one period here, let's say from minus t over 2 to t over 2 for the interval of integration. Another selection can be from 0 to capital T, but when you do from 0 to capital T, you have to integrate from 0 to T1 and from T minus T1 to capital T, two integration intervals. Okay, so that's why you choose the easiest, what is easy for you for the interval of integration. So here we select from positive t over 2 to minus t over 2. Further, we minimize because it is 0 as this part and as this part. We minimize to minus t1 to t1. So from minus t1 to t1. Now the first, usually we start with the DC part. DC part means k is equal to 0. When k is equal to 0, the integration of x of t over a period. It's like a sort of the average of the signal, that means, over one period. So A0 will be 1 over t, x of t is 1 between minus t1 and t1. So it will be the integration of dt. The integration of dt is t. From t1 to minus t1 is 2t1. So 2t1 over t, or any t1 and capital T. Okay, so this is A0, the DC part. If k different from 0, and we use the rule of integration for e to the power of at. E to the power of at is 1 over a, e to the power of at. So a is now minus jk omega naught, so negative 1 over jk omega naught e minus jk omega naught t. Then we integrate this, we evaluate from t1 to minus t1, and when we evaluate, we have this. We can change this, simplify this, and change it to sine, because sine is of theta is e raised to j theta minus e raised to minus j theta over 2j. So we can just here take multiply by 2 over 2, and I have here 2j, 2 will cancel 2, and so it will be the same. So this part is sine of an angle, which is the angle is k omega naught times t1, right? So omega naught is 2 pi over t. So sine 2 pi k t1 over t over pi k. So for these rectangular parts, we found the a case where the a0 is 2 over 2 times t1 over t, and the rest of the a case are governed by this equation. So a0 is 2t1 over t, ak sine 2 pi k t1 over t over pi k. If capital T is 8 times t1, 8 times t1, for example, so a naught is 1 over 4, and ak will be sine of pi over 4k over pi k different from 0. Why we say k different from 0 here? Because when k is equal to 0, this will be sine of 0, which is equal to 0, and 0, 0 over 0, undefined. And that's why usually we solve the DC part at the beginning. If you have undefined, you need to use L'Hopital rule from mathematics. So L'Hopital rule, the derivative of this is pi over, by chain rule also, pi over 4 cosine pi over 4k, and the derivative of this with respect to k is pi. So evaluate at k is equal to 0, then you will get a0 1 over 4. Okay, we can use this. In any case now, ak, what is the form of ak? Ak looks like a sinc function. Remember sinc function, sinc of x from mathematics, sine pi x over pi x. So this is a continuous time graph for sinc function, but this one is discrete. Why? Because k are integers. So you can easily plot this actually. You can plot it with MATLAB, for example. You can give k from minus 20 to 20 and then define this function. But you have to force it at k is equal to 0, 1 over 4, and you plot it using a steam command, steam k comma ak. Then you will have the discrete version of this continuous time sinc function. Okay, so I hope you understand these examples, and also in the slide, it's you have more examples also here. Again, the revision of the synthesis and the analysis equation. Read it, and we have more examples. You can see the additional examples also, or you can revise the same example. This is a sinc function. That's what I said. When you plot it using MATLAB as a function of k, it is a discrete version of the sinc function, a discrete version of the sinc function. So you can do it by yourself, this one. Okay, another example is here. I have a periodic impulse train. So this is a periodic impulse train. How we define it? Summation of x of t from n minus infinity to infinity Dirac t minus nt. Okay, this is periodic with period t, capital T. So at 0 I have an impulse, at t I have another impulse, at 2t I have an impulse, and so on. So this is, we call it periodic impulse train, which is used for sampling, ideal sampling actually, of signals, because when you multiply any signal with this impulse, the signal will be defined at the location of the impulse, right? It will have a value at the location of the impulse. That's why it is used for sampling, and it is called a sampling function. So we select one period now, let's say from minus t over 2, and t over 2 to find the x. So the integration 1 over t from capital T over 2 to minus t over 2 x of t times e raised to j k omega naught t dt. Okay, but if we select one period, we have only the impulse, sorry, one period here from minus t over 2 to t over 2. So we have the impulse at the location t is equal to 0. So you have Dirac t times e raised to j k omega naught t. And remember, when you multiply the impulse with any function, the second function will have value at the location of the impulse. Here it will become e power of 0. E power of 0 is 1. So the integration of the impulse, as long as you include it, it will be 1. So the result will be 1 over t. So the x are 1 over t for all k for this periodic impulse train. Then I can write x of t in terms of the x. It will be summation of from k minus infinity to infinity ak e raised to jk omega naught t, where ak is 1 over here. So this is how you reconstruct the impulse again, the impulse train again from the x. All right. So this is again x of t. To summarize, the Fourier series representation is ak. By the way, why we have these two arrows, it means we can go from time domain to frequency domain and find the x. Okay, using the x can be found using the analysis equation, and you can reconstruct x of t. Okay, the analysis equation means this equation. You can reconstruct x of t from the x using the synthesis equation, which is this. So that's why we have two arrows. That means you can go forward or backward. And one last thing, not every periodic signal can be represented as infinite Fourier series. However, all interesting signals, periodic signals, can be represented, especially those signals where they are absolutely integrable over one period. That means the periodic signal should be the integration of the periodic signal over one period should be infinity. And we have here two more conditions. You can read about this. We call them Dirichlet conditions for convergence of Fourier series. Okay, with this, we finish the examples of the Fourier series analysis. And thank you for listening to this lecture, and see you in the next lecture class.